Good afternoon. I would like to welcome you to this webinar on isolation rooms. My name is Blanca Beato and I'm the microclimate team leader of BSRIA test. This is the first of two webinars on isolation rooms, and it's going to deal with isolation rooms in general, the ventilation of isolation rooms, and the tests that BSRIA has carried out to validate designs. The second webinar, which is tomorrow, is going to deal specifically with air tightness in isolation rooms and how to do a test. Nowadays, I think there is no need to clarify why we need isolation on certain occasions. And the items that we're going to talk about today are a brief introduction to pathogens and disease transmission, what engineers can do against airborne infection, and what types of isolation rooms there are, how BSRIA has tested and validated designs of isolation rooms and the results that were obtained from the testing, what is next or what to do with an isolation room next, and finally the conclusions to the presentation. Well, to begin with, there are 4 category levels or biosafety levels of pathogens. From 1, which are pathogens that do not ordinarily cause human disease, 2, which are pathogens that can cause human disease but whose potential for transmission is limited, 3 are those infections that can be transmitted through the respiratory route, which can be severe to fatal in humans, but there are vaccines or other treatments, and 4 would be exotic agents, for example, Ebola. The latest information that I have read about coronavirus is that it's being dealt with in category 3 laboratories, and CDC has also allowed category 2 laboratories to deal with this virus with a whole lot of special additions and conditions for testing. When it comes to isolation rooms, laboratories, and on some occasions operating theaters, they are also classified in accordance with the pathogens that they are able to contain or the pathogens that they are able to be analyzed in a laboratory. So what you can see on the left-hand side is actually a category 2 to category 3 isolation room, which is also an intensive care unit. What you see on the bed and surrounding the bed is DINMEN or people simulators, and you can also see a lot of equipment that is necessary in the room because it was an intensive care unit. Simulating the heat loads in the room is very important when we are validating the rooms, and simulating people is actually very important because when we simulate airborne infection using gas tracer tests, which I'm going to talk about in this presentation, the gas originally goes upwards due to the heat load from the plume from a human simulator. What you see on the right hand side is an isolation room for Ebola, so that you see that the patient is inside the Trexa tent, and people are there wearing respirators. Just to say that the design for these 2 rooms has to be different. The next item on the agenda was the types of transmission. Well, there are several ways that an infection can be transmitted, and the most common ones are these 4 here. Direct contact is when a person gets in direct contact with an infected person. Indirect contact is when we touch a surface that has been contaminated, and then perhaps we touch our face. This is why it's so important nowadays to wash our hands at every opportunity. The third one, airborne transmission, and the fourth one via droplet. Sometimes some authors, they classify them as together. Some authors classify them separately, and there is some debate about them. Droplets are a little bit bigger and they tend to fall to the floor, and airborne transmission are infections that can be transmitted via the air. And this is what the isolation rooms that we're going to talk about in this presentation are about. As engineers, we can fight infection using ventilation. We need to focus on what happens inside the room when staff and visitors come in. And we need to focus on how to separate the air between the room and the rest of the hospital so that there is no infection transmission either way. When it comes to the air in the room, the air in the room is used to remove contaminants, heat loads, and others. There are many ways to ventilate the room depending on which isolation room category we're in and what we're trying to do. For example, what we have here is an example of piston flow, which is used in operating theaters because we want to have fresh air into the operating table at a certain speed. And this piston flow is used in some category 4 isolation facilities where we want the staff to be in the path of fresh air and not exposed to any contaminated air whatsoever. And this is also used in anesthetic rooms where we don't want any anesthetic gas that may leak to get into the respiratory area of the surgeon and the staff. Here's an example of a well-mixed room. So what you see here is that the air in the room is well-mixed, and so are the contaminants. So what the air is doing is diluting the contaminant concentration in the room so that the staff do not get the infection dose, even though they will also be wearing PPE. If we focus on the ventilation between the room and the rest of the hospital, and if we think of a balloon, we inflate a balloon and we let it go, we all know that the air is going to go from inside the balloon into the outside, which leads us to two basic engineering principles that we use for isolation rooms, which are that the air travels from higher pressure areas to lower pressure areas, and that air will find any gap to escape from a high pressure area, including the walls. This is why air tightness is so important. So if we have a patient who is immunocompromised, we would put the patient into a positive isolation room, which is at a higher pressure than the rest of the hospital. Therefore, the air will travel from the isolation room into the rest of the hospital. And on the other hand, if we would like to contain an airborne infection, you would think that what we should do is put the patient into a negative isolation room because the air from the rest of the hospital would go into the isolation room because it's at a lower pressure. This is a good idea for laboratories, for example. However, you have to think that a patient who is in an isolation room should also be protected from another infection occurring in the rest of the hospital. And this is where a positively pressurized ventilated lobby comes into play. So a PPVL, or a positively pressurized ventilated lobby, is a space or an airlock that is at a higher pressure than the rest of the hospital and also at a higher pressure than the isolation room. So the air will go from the lobby into the isolation room and from the lobby into the rest of the hospital, stopping any air going from the rest of the hospital into the isolation room or the other way around. This is a type of isolation room that can be used for both immunocompromised patients or infectious patients or patients that have not been diagnosed yet, but you suspect that they may have a contagious infection, because these rooms actually protect the patient and they stop the air from the isolation room traveling to the rest of the hospital. This is an example of the room tested for the Department of Health, and it consists of a lobby, an isolation room, and an ensuite. And how it works can be seen in this schematic here. So you have the lobby, the patient's room, and the ensuite bathroom. The air is supplied mechanically into the lobby. The lobby is pressurized, and the air change rate in the lobby is as high as 60 air changes per hour because it's a relatively small space. And some air will go from the lobby through the door gaps into the corridor and through the lobby to isolation room door into the isolation room. But most of the air is designed to go through a pressure stabilizer into the room. The air in the room mixes and it dilutes the concentration of contaminants, and then is extracted through a grill on the door of the ensuite, which is at a slightly lower pressure, minus 10 pascals, and then it's extracted and HEPA filtered and extracted to outside. A second example of another isolation room is actually the critical care isolation room, which I showed you before, which has the same principle. It has a positively pressurized ventilated lobby, which is at a higher pressure than the corridor and than the isolation room. There are a couple of pressure stabilizers that supply the air into the room. They mix the air, they dilute the contaminants, and then the air is extracted into the plant room. This room had its dedicated plant room. It had no en-suite because it was an intensive care unit, so it wasn't needed. This next slide shows how BSRIA validates the rooms. The validation process consists of several steps. We would first get it designed and we will build the mock-up, or we would actually go on site and test there. Then we would do an air tightness test, a smoke test, room air movement tests or anemometry tests, gas tracer tests, which are the ones that we use to simulate an airborne infection, and salt tests or biological tests, which were actually carried out by the University of Leeds, and finally CFD. The first step on the validation process would be to build the isolation room. If you have a design which you cannot build, then you should go back to the design stage. And also, when you build the mock-up, you realize that you can identify the problems and use the lessons learned to build the next 20 of these isolation rooms. The second thing that we would do would be an air tightness test, which consists in measuring how leaky the room is. And after testing several isolation rooms, BSRIA has published a technical standard that is free. You can download it for free from our webpage. And this is what the webinar is going to be about tomorrow. Air tightness is really important because in the event of fan failure, the walls are the first line of defense. So if the air escapes through gaps into other hospital areas, you have contaminated air that is leaking into areas where you would think that you don't need PPE. Therefore, the gaps and the air permeability should be as small as possible. The next step in the validation process will be to carry out smoke testing, which is a very easy way to see what the air is doing. What you see here is we are inside the isolation room and we are releasing smoke near the pressure stabilizer. And perhaps you can't see it, but the video is getting a bit blurry. And this is because the room is well mixed. So it means that the smoke gets everywhere. Smoke is a very good tool to identify how the air in the room is moving. And you don't need to have a big smoke generator like this one. You can also have a pencil smoke generator, which nowadays could be very useful to identify if a room is positively or negatively pressurized, or if you need to adapt other areas of the hospital quickly. The next step in the validation process is anemometry tests, which consist on building a pole of anemometers and moving the pole through a grid that we mark on the floor, and we would measure the airspeed and the air temperature in different points in the room. We also use anemometry tests to calculate the thermal comfort of both the staff and the patient. And this is an example of how the results can look. The physical measurements can be interpolated and it gives you a profile of the air through the rooms. So what we have here will be the lobby, the isolation room, and the en-suite. And what you can see here in pink is the jet from the pressure stabilizer coming into the room, what we saw in the smoke test, which, by the way, did not cause any discomfort to the patient because the patient bed was not in its path. We also carried out computational fluid dynamic tests, although to model the pressure stabilizer, we had to use physical measurements from the anemometers to input into the CFD model and achieve the same results that we were obtaining with the physical mockups. Now, as I mentioned before, if you're going to deal with pathogens, you need to be a category 2, 3, or 4 laboratory. And at BSRIA, we're not a biological laboratory. That's why to simulate an airborne infection, we do gas tracer tests. A gas tracer test consists on releasing nitrous oxide in order to simulate an airborne infection. And what we do is we measure the concentration at different points in the room and outside the room. This is an example of some of the points which were monitored, where we monitored the concentration of gas. And what we see here is that we measure the concentration in different points in the room, near the patient, different points outside the room. And we measure it in the supply, near the lobby, by the doors, in the extract. And we did a series of tests. We checked how the room would work during normal operation with the doors closed, and we checked what would happen if the patient was the infectious one. So we would release pure nitrous oxide from the patient's bed, from the DINMEN or people simulator that we use as a patient, and we would measure the concentration in different areas of the room and also outside the hospital corridor. And we also did the reverse tests. So if the patient is immunocompromised, we would release gas outside the isolation room and checked if we got any nitrous oxide inside the room. And then once we checked how the room works under normal operation, we did some what-if scenarios. What would happen if we tried a different pressure? What would happen if we tried if a member of staff forgot the doors from the lobby into the isolation room open, or if they were open and closed continuously? What would happen if we leave the en-suite door open? If the supply fan fails, what happens if the extract fan fails? And here you can see an example of a gas tracer test. So let me take you through the results. So when we start releasing gas, so when a patient is put in the isolation room and they begin to release pathogens, because of the ventilation system, eventually we achieve a steady state. The concentration of contaminants does not go up and up forever. It achieves a steady state. A steady state. What happened here, and the sudden drop of concentration, was because we opened the door to the lobby on purpose, and we left it open. So what we see is a sudden drop of concentration, because suddenly we are sharing the same amount of contaminants between a larger area, which is the lobby and the patient's room. And then we saw that the room stabilized again. And this is what happened. This small curve here is what happened when the ventilation was increased just a little bit. When we close the door from the lobby into the patient's room, suddenly we get a peak. And this is because, as I mentioned before, the lobby has a really high air change rate. So it means it purges contaminants really quickly. So all the contaminants went through the pressure stabilizer and gaps through the doors outside and into the room. And that's why we suddenly got a higher concentration of contaminants. And then we would achieve a steady state that was very similar in concentration to the original state. And what happened here at the end is we stopped releasing gas. So with measuring the decay in the room, we're able to measure what the air change rate is in the room, which may differ from the mechanical air change rate, because some areas will be not so well mixed. Some isolation rooms may have some kind of short circuiting. So if you think that your air change rate is 10 air changes per hour, perhaps you would like to do a gas tracer test, and you may be surprised at the results of what the effective air change rate in your room is. And finally, we did some biological tests at the University of Leeds because they have a biological laboratory to do these kind of tests. We did some tests using Bacillus subtilis, which is actually a category 1 pathogen. So there was no risk to the people doing the test. But actually, Bacillus subtilis is a substitute for anthrax when you do this type of testing, when you do this type of analysis. So what we did is we repeated the same tests with gas tracer tests and with real aerosolized pathogens, and we compared how well the nitrous oxide and real pathogens behave in terms of concentration. So the next item on the agenda was to see the results from the testing that we did on isolation rooms. Results showed that during normal operation, the rooms actually worked very well in protecting the patient, in protecting the staff, and in protecting the rest of the hospital, or in isolating the room from the rest of the hospital. The rooms were well mixed, which means that no member of staff would get a higher concentration or a higher dose of infection, for example, on the left-hand side of the bed or on the right-hand side of the bed. And pathogens were diluted up to 10 to the 4th, which reduces the infection dose. The 10 to the 4, what it means is we were releasing pure nitrous oxide, so 10 to the 6 ppm. And the concentrations that we were measuring were 85 ppm, 120, 130 in the extract ppm. So that's a dilution factor of 10 to the 4 inside the room. And outside the room, we were measuring a nitrous oxide concentration that was smaller than the lower detectable limit of our instrumentation. So you could say that the protection was 10 to the 5, 10 to the 6 outside. But we also did loads of what-if tests. What would happen if a fan broke, if we opened doors continuously, if we modify the pressures, if we left doors open, if we put the pressure stabilizer in a different place, if we use high extract or low extract in the case of the ICU. And then what we saw is that the beauty of these rooms was that they actually recovered pretty well from all of these what-if tests. In a few minutes, the room would go back to normal operation. So what's next? What to do next when you have an isolation room perfectly validated and commissioned and tested? So the idea would be that everybody who is going to use the room, including the patient, must be trained on how the room works. And this should not be complicated. This is just to create a simple protocol so that everybody understands that the rooms work when the doors are closed. That's when they work better, that they shouldn't block extracts or supplies with other hospital equipment, that the patient should stay in the room and they shouldn't go outside of the hospital for a smoke, as unfortunately we've seen this happen. And we can apply the positively pressurized ventilated lobby concept to other hospital areas that we might need in times of coronavirus. We can adapt new spaces to create more isolation spaces with this theory. So to sum up this presentation, we've seen today what types of infection and transmission there are, how ventilation works in isolation rooms, how we use pressure differentials and air tightness to protect against airborne infection and to separate the air from the room and from from the rest of the hospital. We have seen that within the room, pressure differentials are not the important thing, but the way that you ventilate the room is the important thing. And we've seen that these rooms work on dilution and good mixing to protect against infection. And we have seen how the the rooms are validated, how it's very important to commission them, and how important it is to use this room properly. And hopefully this presentation can inspire some designers into applying these principles and to see what can be how these principles can be applied to the current situation that we're facing now. That's the end of the presentation for today. You're very welcome to join us tomorrow for the presentation that is going to be specifically on how to calculate the airtightness of the isolation room. And if you have any questions, you can send me an email to that email address, and I'll try to answer all of your questions. You can send me an email anytime.